Hello everyone, welcome to the lecture series on Foundations of Deep Learning, Concepts and Applications. We had started with Explainable AI in this particular week, and in the previous session we had seen guided backpropagation algorithm with the mathematical foundation. In today's session we will explore Grad-CAM and then CAMs. CAM here is a class activation maps. So, before we go into details of Grad-CAM and CAM, in the interest of learners here, I would like to explain you one concept. Whenever we are applying the explainable AI methods, we will be why is that we will be requiring an explainable AI? In order to understand which are the features which has actually contributed for models prediction. So, suppose if you are using the underlying model here as a CNN, if you are if you want to interpret the results of an images, the underlying architecture will be CNN model. So, CNN model here will be already fully trained. What is the meaning of this particular line? Now, whenever we build a CNN model, we are going to build a model, after that we are going to compile it and then we are going to train the model. And during end of the training, we will be seeing what is the training accuracy and then what is the training loss. So, this will give us the clarity of how well the model is being trained. And once you freeze the model, meaning once you feel that the model is well trained, ideally the meaning of it is we have got an optimized kernels, so that it can extract very good features. Then in CNN we have dense layers, so the weights of all these dense layers are optimized and even the biases. So, once the model is well trained, then during testing the input image is being passed. Now, input image is passed to this trained CNN model. Now, once the image is being passed, for that particular image the model is going to give a prediction. So, model produces the prediction. Suppose if you are dealing with an animal data set, it is going to say whether a given animal is a cat, a dog, or if you are dealing with any medical images, whether a particular tumor is cancerous tumor, benign tumor or border case, it is going to give us the prediction. Now, once the prediction is being made, what is our goal now? Now, the goal is to understand which are the features which has actually contributed for this particular result. But unfortunately, the CNN cannot do it. CNN cannot tell which are the features that have been contributed. Therefore, we will now apply an explainable AI techniques. So far we have already seen guided backpropagation. So, today in this particular session we will see Grad-CAM and the CAMs, how these two are used for the explanation. Why this particular slide is being explained here? Often the students or the learners here will get confused, because we are using the word in the previous session guided backpropagation and here the gradient. So, are we doing any weight updation here? The answer is no. Although there are words backpropagation, guided backpropagation, gradient, we are not updating any weights or anything here. Already the model is well trained, CNN model is trained. To that trained CNN model, we are passing one test sample. The prediction which is made for that test sample, we want to understand which are the features that have contributed. So, for that we are applying the explainable AI concepts, but just because of the word gradient or guided backpropagation, there is no weight updation that is taking place at this point of time. So, here we are only trying to understand, okay, the model has made this prediction, which features actually contributed for this prediction. So, that is all is what we are doing it. So, in order to identify which features, we are calculating the gradients or we are doing the backpropagation. So, I hope this one concept, fundamental basic concept is clear. So, let us get started with the topic for today's discussion, that is Grad-CAM. So, what exactly is the full form of Grad-CAM? Grad-CAM stands for gradient weighted. So, grad here is gradient weighted and the CAM here is class activation mapping. So, in short we will call it as a Grad-CAM, which is a gradient weighted class activation mapping. And what exactly is this particular Grad-CAM? It is a model specific XAI method. So, it is important why exactly we are specifying it as a model specific. So, Grad-CAM is a model specific XAI method. So, how exactly XAI works? So, let us get into. Now, if you look into this particular diagram, this is an input image. During a testing you have passed an input image. Now, this input image will go through the entire CNN model. So, at when you say CNN model, you will reach to convolutional layers. Now, from week 3 contents of this particular course, we have seen how exactly the convolution works. So, on this input image, we apply the kernels. Now, if you apply 3 kernels here, we are going to get 3 feature maps. If you apply 4 kernels, we are going to get 4 feature maps. If you apply 5 kernels, we are going to get 5 feature maps. So, here we have applied 3 different kernels. So, this is an input image. We have applied 3 different 3 kernels and we have got 3 feature maps. Now, when you perform a convolution operation, the kernel will go through the entire image and then you are performing an convoluted operation and we get a feature map. So, which means in the feature map we have values in each of these places. So, what is this value? It is an multiplication and then you are adding up the values. So, you are going to have a value in each of these places. So, those values we call it as an activations. So, the value inside the feature map we call it as an activations, and every of this feature map we call it as a channel. So, one feature map is one channel. Since there are 3 feature maps, there are 3 channels here. So, this is something fundamental which we have recalled from our CNN. Now, our point of discussion is Grad-CAM. So, what exactly Grad-CAM does? Grad-CAM depends on the internal components of a CNN. What are internal components? Grad-CAM requires this last convolution layer. The meaning of last convolution layer is, in CNN, after convolution layer we have the flattened layer. So, just before the flattened layer, the last convolution layer, Grad-CAM is going to use that last convolution layer. So, we require the convolution layer, and in the convolution layer Grad-CAM also uses the feature maps. Which feature maps? Once again, the feature maps of the last convolution layer only, the feature map in those layer, and it Grad-CAM also uses the values of all of these feature maps, that is channel wise activations. Why is that? We have written here post ReLU. Soon after we get the feature map, we are going to pass it to ReLU, so that in the feature map, if at all if there are any negative values, ReLU is going to remove all those negative and make it as 0. So, that now these feature maps are having only 0 and positive values. So, Grad-CAM also depends on the values here, and the Grad-CAM depends on the gradient flowing through these layers. So, Grad-CAM depends on internal components. When we say internal components, the final convolution layer and then the feature maps that are produced from this final convolution layer, and the values inside each of these feature maps, and the gradients which are flowing through this layer. Okay. So, this is what the Grad-CAM depends on. Now, let us try to understand what is this model specific XAI. Grad-CAM works only on CNN based models. Now, we have so far we have seen many neural networks. We have seen ANN, that is multi-layer perceptron. Then in the going forward we will be seeing sequence to sequence models. Then we have seen CNN. So Grad-CAM is an explainable AI technique that works especially only on CNN based models only. That is the reason it is called model specific XAI method. Why it works only on CNN based? What is the reason behind? Because Grad-CAM needs to access to all of these internal components. Which are those internal components? It requires the convolutional layers, then it requires the feature maps of that convolution, the last convolution, then the values which are there inside these feature maps, and then the gradients. Now, if you look into among all the models that we have discussed so far, that is ANN and CNN, is it not, it is the only CNN which produces these feature maps to us? Is it not the yes, it is only the CNN which produces the feature maps. That is the reason Grad-CAM works only on CNN based model. That exactly is called model specific. So with this, let us formally see what exactly is the definition of Grad-CAM. So Grad-CAM is an explainable AI technique that is going to, if you look into this image, that is going to highlight the regions in the image that are most important for models classification. So it is going to highlight the region of an input image. Now, how it is going to do this? It is going to compute the gradient. This is very, very important. It is going to compute the gradient of class logit with respect to the feature maps in the final convolutional layer. So let us understand this particular line in the coming slides, but as of now you only try to remember that Grad-CAM is an XAI technique that is going to highlight the features that are more important for model prediction by computing the gradients. Now, when you say the gradient is always how the output changes when you are doing some change to the input. So here how we are computing the gradients? We are computing the gradients by using the class logit. And with respect to what? With respect to the feature map values of last convolutional layer only. That is an important point here. So with this, let us try to understand what is the working mechanism of Grad-CAM. So this is what is the working mechanism. So now the CNN model is well trained. Now to that well trained CNN model, you are passing the image. During a testing phase, you are passing an image. Now let us look into the forward pass. So what exactly happens? Now let us assume this is an input image that you are passing it into the CNN model. This input image will first go into the first CNN, first convolutional layer, then it goes to the second convolutional layer, and it reaches to the last convolutional layer. In the last convolutional, for the last convolutional layer, let us assume there are 5 kernels that we are using. When there are 5 kernels that is applied onto this input image which has reached to this last convolutional layer, now onto this, when kernels are applied onto this whatever the input that has reached, we are going to get the 5 feature maps. Why 5 feature maps here only? Here k is 5. Why it is 5? Because we have used 5 kernels, therefore we are going to get 5 feature maps. Now, what is the next step? We are going to combine all of these feature maps and then pass it to the flattened layer. We are then passing it to flattened layer. From the flattened layer, we are passing it to the dense layers, and in the dense layer, we have defined the final output layer. And if at all, if it is a multi-class classification problem, the final layer, the output layer will have if it is a 4 class problem, for example, we will be using a 4 number of neurons and we are using a softmax activation function. The most important point here is, now for this particular input image that is passed to this CNN, let us assume the model has predicted that it belongs to this particular class. It belongs to this class. Now, what we are going to do, to which class the model has predicted this particular input, we are going to take something called YC. We are going to take YC. What is this YC? YC is an logit. Now, what exactly is this? Now, you will get one value. Onto this particular, at the output layer we are going to get one value. Onto this value we will be passing it to an softmax activation function. If you have 4 neurons at an output layer, suppose if you have 4 neurons at an output layer, now before you pass it to an activation function, summation and activation, summation activation. So, before you pass it to your activation function, suppose if the model has predicted this particular class, we are going to take this summation 1. So, this is called an logit. So, what is a logit? It is an value before applying the activation function at the output layer. So, we are interested in getting that particular value. So, let us assume that value is YC. Okay. Now, what is YC here once again? Now, which for a given input, if a model has predicted a particular class, let us assume the model has predicted a particular class C, that the particular class logit, that is before the activation function. So, that is what is YC, which is an value before an softmax, that is the pre-softmax score. So, we are going to require, we take this YC. Now, the most important question is, why are we focusing only on the last convolutional layer? So, let us try to understand why the focus is only towards the last layer. Why not at the beginning layers? Why? What is the reason? The reason here is, now we know once again from our week 3 content, when an image is passed to an CNN model, especially when it reaches to the first convolutional layer, it focuses on extracting only the simple features. It can be lines, edges. Then when it goes into further convolutional layers, that is mid convolutional layers, it focuses only on extracting the textures. But when it reaches to the last convolution layer, this is the layer which is responsible for high level features, which means the feature maps which are obtained from this last convolutional layer is typically having the high level and rich features are present. So, in all of these feature maps, we have high level rich features are present. What is our aim? Our aim is to identify which are the features which has contributed for model's prediction. Then if this is the layer which is having the rich features, then obviously we will be considering this particular feature maps of last convolutional layer only. So, this is what is the forward pass. Now, let us get into, so from the end of the forward pass, what is that we have obtained? We have obtained the feature maps from the final convolutional layer, and then we also got the output score, that is YC. And what is YC? It is the value before the softmax. So, what we have done so far, CNN model is a trained CNN model. To that now one image is passed during testing, and during testing whatever the image that is passed, it is going through the entire CNN model. At the final output layer, we have got the prediction for this particular input image that is passed. Now, we want to identify why the model has made this particular prediction. Now, let us look into the core working mechanism. Now, in the forward pass, we have got these values. Now, let us see what is going to happen the next. So, in the forward pass, we have got the feature maps of the final convolutional layer. So, let us assume these are the feature maps A1, A2 and so on up to AK. If at all, if we have used the 5 kernels, we are going to have 5 feature maps. In general, if you are using k number of kernels, we are going to get k feature maps. Now, and we are also going, we also have this particular value yc. Now, what is the important? The model has predicted that a particular input belongs to this class, a target class, and we have yc value. Now, our aim is to understand which are the features which was responsible for model prediction. That is the reason we are using a Grad-CAM. Now, what Grad-CAM will do? Grad-CAM will tell the CNN that compute the gradients. So, come back and back propagate and compute the gradients. Now, when it tells the CNN to compute the gradients, what CNN will do? CNN will come through the backward pass, and in the backward pass it is going to compute the gradients at a dense layer also, and then it comes back. When it comes back, it is going to compute the gradients at the dense layer, it is going to compute the gradient at a flattened layer, and then it is going to compute the gradients of each of these feature maps. But Grad-CAM does not care about the gradients at a dense layer, does not care about the gradients at an flattened layer. It only requires the gradients of these feature maps only. Although in the backward pass, we are going to get the gradients at the dense layer, and then we are going to get the gradients at a flattened layer, Grad-CAM does not use these, do not care these values. Then what is that Grad-CAM requires? Grad-CAM requires only the gradients of each of these feature maps. Now, how it is going to calculate for example, let us take an A1. This is the feature map, and these are the values of this particular feature map. Now, what we already have, we have this yc. Yc, what is yc? Yc is the predicted value class score. For a particular input, you are finding out which features are important. So, whatever the model which has predicted for that particular input image, we are taking the yc of it. And we are going to compute the gradient. How is that we compute the gradient? We are computing the gradient of yc with respect to every value of the feature map. So, here since we are doing it for A1, it is going to compute the gradients of every of these values. Say for example, we have gradients. By computing this, let us assume we have got this particular matrix. Now, what is this matrix tells? It tells how much does changing the location, changing each of these values in the feature map affect the score of the class C. That is what is this gradient tells us. So, what did we do? It is very simple. In the forward pass, we have got the feature maps, and then we have got the yc. Now, in your Grad-CAM tells the CNN that give me the gradients. So, how CNN does? CNN now will come in the backward. In the backward, it is going to give the gradients of dense layer and then the flattened layer, but Grad-CAM does not require any of those. And the CNN, when it comes backward further, it also gives the gradients of each of these feature maps. For understanding, we are taking one feature map. If this is the values of the feature map, we are going to obtain the gradients of it. How are we calculating the gradient? It is the derivative of this class score yc with respect to every of the value here. Then we obtain this. Then the next step is calculate the weight. How is that you will calculate the weight? This is the formula to calculate the weight. Now, what is the this particular formula? Add up each of the values, add up all the values which are here, and then divide it with the number of elements which are present. So, it is I is a row, j is a column. When I is 0, j is 0, we are taking this value. When I is 0, j is 1, we take this value. When I is 0, j is 2, we take up this value, and so on so forth. When I is 1 and j is 0, we take this value, so on so forth. You take each of these values and you will add up all of these values, divide it with the number of elements that are present in this entire feature map. Now, what exactly is this z? Z is height and width. What is the height of this? What is the width? That will give us the number of elements that are present. So, we are going to get the weights of it. So, we are computing A1. So, what is A1 here? The weight of the feature map A1. So, what is this weight tells? How important is this feature map for the class output? So, next. One more important point here is, once whatever the weights that we are going to get, those weights, how the weights values we are computing, we are adding up all of this and then we are taking the, we are dividing it with number of elements. If the gradient values in every of these location are all positive and if the values are high, then the weight that we are going to, the score of this will be high. If all the values, if most of the values in each of these locations are negative, then we are going to get a smaller weights. So, that is what is this particular explanation that is given. If the gradient is large and positive, then this feature is very important and thus gets the larger weight. If the gradients, if all of these gradients are small or negative, then we are going to get a smaller weights. So, let us see that with an example. Let us assume this is one feature map and these are the gradient values, and then we are going to add up all of these values. We will add up all of these values and you will divide it with the number of elements. What is number of elements here? Height and width. Height is 5 and width is 5. So, 5 into 5, 25. So, A1 what we are getting is 0.132. Similar way, let us assume this is the second feature and these are the gradients of second feature. I am just giving an example here for a better understanding. If you look into the second feature gradients, there are so many negative values, and if you look into the first one, you just have only one negative value. Here there are many negative values. So, we have got this particular weight. How is that you are calculating? Once again, add up each of these values and then divide it with the 25. Then take the third feature map, and if you look into the third feature map, every of the values which are present here are all positive values only, and therefore, when you compute the weight, you got the larger weight. That is what we have seen, that if the gradients are large and positive, that particular feature is important and it is going to get the larger weight. So, if you see all these gradients are all positive, therefore, you got the higher weight, and here you have so many negative values and you got lesser weight. And what is the meaning of these weights? If A3 weight is more, it means the feature map A3 is having more importance, then feature map A1 is having the important, then the feature map A2. So, A3, A1 and A2. This is the order of a feature map importance. Then the next step in a Grad-CAM is we have to compute the heat maps. How is that we compute the heat maps? What is that we have done? We have calculated the weights. So, now the next step is do the multiplication. How is that you do? you will multiply each of the feature map by its weight. You will take this A1 and multiply it with this. So, the operation that you do is A1 get multiplied with this feature map, A2 gets multiplied with this feature map. Similar way, AK is the weight which gets multiplied with this feature map AK. So, once you multiply, is it not again we get one matrix, one feature map? So, this is a feature map, and when you multiply weight with each of these elements, once again we are going to get a feature map. Then we are going to do an element wise addition. We are going to perform an element wise addition, and finally we are going to get this particular matrix. Now, if you look into, so what operation we did? We have computed the localization map, and how did we do? We have taken the weight and then we have multiplied it with its feature map AK. So, and then we are doing an element wise addition. Summation, we are doing element wise addition. First we are performing multiplication, then we are performing an element wise addition. Then you are seeing that there are so many negative values also, but we are only interested in which are the features which have contributed for model prediction. Only we are interested in positive values. How do we get the positive values? How do we eliminate the negative values? Apply ReLU. Pass this entire matrix to ReLU. So, is it not to this formula now we have applied ReLU? Right. So, when we apply ReLU, all the negative values becomes 0 and positive values are retained. Now, apply some color encoding and then see something like this. All the features which are zeros give lesser and the values which are higher give a brighter color. So, now whatever we have obtained, this is the heat map, Grad-CAM heat map. So, what is this heat map is saying? The heat map is saying which are the pixels which are actually contributing for model prediction. This is the pixel which is contributing for all these bright are the one which are contributing, zeros are all one which is not at all contributing, and these two are having lesser contribution. So, let us see with an example what we have done. We have a feature map A1, A2 and A3, and these are the weights that we have computed. First step is you will calculate A1 with the weight with this feature map. So, this is the matrix. Then this value with the feature map. We are going to get each of these values. Then we are going to do an element wise addition. This value is added to this to added to all these three values are being added, and this is what is the value. These values have been added and you get this value. Like this you perform an element wise addition. Once you get an element wise addition, this is the final feature map. Here coincidentally all the values have become positive, but otherwise if at all if there are any negative values, so pass it to ReLU so that you are going to get the final Grad-CAM values. So, ReLU removes all the negative values, keeping only the positive contribution. Here, since all the values are all greater than 0, all the pixels are all positively contributing. Higher the values, strong features that are supporting, and smaller the values, these are weak evidence. If there are any zeros, then those zeros are not at all, those pixel values are not at all contributing. This is how you will interpret the Grad-CAM heat map. And the final step here is, now if you look into, if this is the original image that we have taken, and if this is the Grad-CAM heat map it has produced. Now, if you look into, by the time you come to the last, by the time you completed it, the feature map size has reduced. Why is that the feature map size has reduced? Because we are taking the final convolutional, last convolution layer, last convolution layer heat map. Now, by the time you reach to the last convolution layer, definitely the input size has reduced, the feature map size has been reduced. That is the reason you are taking the Grad-CAM, that is the reason the heat map size is smaller. Now what you are going to do? We are going to upscale it. So this is what is the output, we are going to upscale. How is that you will rescale or upsample? We are going to, any of the technique can be applied and then increase the size of this Grad-CAM. Then whatever is the upsampled that we have got, that we are going to put it back onto this original image. This, when you put it onto this original image, this is what is the the final output of Grad-CAM. It is going to highlight the regions that are important. Now, one more fundamental, this is the end of Grad-CAM explanation. One more question, basic question that one can get here is, why is that we are focusing only on the final layer only? Because just because the final layer is having rich features, why not consider flattened layer, after flattened layer, dense layer? Why not? Because the final feature maps only are passed to dense layer. Why not focus on those dense layers? Why are we focusing only on final convolution layer? This is important point. Look into. Ultimately, how did we get the output? We got the output as the feature map size only. This is the heat map it has generated. This heat map we have expanded and we have got this, and this is applied onto this input image, or this is superimposed onto original image, and we got this output. If you look into this, now when you apply a flatten, you will no more have something in terms of height and width. You will not have something of this nature when you apply flatten. Flatten converts back into a single vector. But I want something, Grad-CAM wants something in this particular only. That is the reason we are focusing on the final convolutional layer feature map, but not on dense layers, not on the flattened layer. So that is the explanation which is given here. Grad-CAM needs a spatial feature maps only. Why spatial feature map? This is a spatial feature map. Why? Because ultimately this, when you expand, you get this image, and this when you superimpose, you can clearly visualize which features are more important, which features are less important. So when you do flatten, you will no more get something in this matrix form. You don't get this. And where is that, where are these matrix, or where are these feature maps? The feature maps are there at a final convolution layer only. I hope this is clear to you. With this, let us get into the next topic called working of CAMs. This is most of the concepts here are same as the previous. Let me only highlight where there is a change. Now, during the testing phase, you have passed one image, and that image is passed to CNN, and then you are taking the final convolution layer, you are taking the feature maps of last convolution layer only. Then what we are going to do, we have to pass this to flatten layer, but I am not interested to pass it to flatten layer, because a flatten layer will disturb that spatial information. What is that spatial information? Something in the form of height and width. So I want something still in the form of height and width. So flatten layer is going to we are going to lose that particular information. So something which is in the matrix form, we are going to lose it. Therefore, CAMs are going to do one change here. It is not using the flatten layer. Instead of a flatten layer, it is going to calculate something called as global average pooling. What is global average pooling? We have the feature map here. Take the values, add all of these values, and then divide with the number of elements. We are going to get one value, that one value is this. Then take this particular feature map, add up all of these values, divide it with number of elements, we get this. Similar way, This is the global average pooling. How did you do the global average pooling? It is adding up of all of the elements which are there in the particular feature map and dividing it with the number of elements. So then instead of a flattened layer passing, now you will pass this and you look into, if at all, if it is a multi-class classification, if there are 4 classes, we have 4 neurons. So directly this global average pooling values are passed to the fully connected layers. It is passed to fully connected. This is the CNN architecture. The underlying CNN architecture should be this. Now, what is the change here? Now, how the CNN model is built for CAMs? CNN model here is up to convolution layer, it is correct. But here we are not using a flattened layer. We are using global average pooling. After that, we are using only one single fully connected layer, and that one single is the output layer. We are using this. So this is when an input is passed, the model is giving a prediction. Let us assume the model has predicted this particular class. So CAMs are something which works for a special type of CNN. What is this special type of CNN? A CNN where there are convolutional layers, there is an global average pooling and a single fully connected layer only. This is something very, very restrictive one. So the modern architectures, if you take like ResNet or any of the modern architectures, doesn't use an single layer. Even if you take VGG16, it has 2 dense layers and then the number of neurons in the dense layer is 4096. But in such architecture, CAM's explainable AI method cannot be used. Why? CAMs works only for those CNN models which are having any number of convolutional layers, then global average pooling and a single fully connected. So this is how the CNN architecture will be. So during a testing, you have passed a single image. It is going through the entire of this architecture. It is going through the entire of this architecture. Finally, for this input image, suppose the model has predicted this. So let's see, for that particular image, let us assume the model has predicted one particular class. Now, how the calculations takes place? Is it not when it comes to fully connected, is it not the calculation will be something like this? You have 5 different features. This feature, if it is connected to this, here you will be multiplying with this weight, this with this weight, and this with this weight, and this feature with this weight, and finally it is with this weight. So look into, is it not a simple Wx plus b is what we have calculated here. Here, since number of features are 5, there are 5 such terms. Similar way, for every of the neuron, is it not this is the calculation that is being done? Now, for that particular input what you have passed during a testing, how is that you will see which class? Is it not for whichever the value is high, for whichever the maximum value, that is the predicted class. Now, that predicted class you will take YC. That is, suppose if this is the class that the model has predicted, you will take this value. This is what is YC. So, if you look into the calculations, so whatever the class that the model has predicted, suppose if for that particular input, if the model has predicted this class, then the weights that are associated for that particular, what are the weights that are associated? Is it not this is the weight, the one which is highlighted? It is these weights that were responsible for this particular neuron. So CAMS uses only those weights. Which weights? The one which has predicted. Now this is this neuron is where you got the output. So here is where you have the maximum predicted value, and that class score you are going to take, and its associated weights is what the model is going to, the CAM is going to take it. Right. So, mathematically, is it not this calculation? YC is weight multiplied with the output of GAP, GAP applied on each of these feature maps, you get G1, G2, G3, G4 and G5. So, this is when it is applied on each of these activation each of the feature maps, you get one value. So, you are multiplying weight with G values and bias. Then what exactly is global average pooling? Is it not the global average pooling the formula is this? So, when you apply this formula into this, is it not we get? It is just the formula which has been substituted. We know GAP is global average pooling is adding up all the values and dividing it. Now, in this particular place, we have substituted GAP value. Then you have this part and the whole of this, and you have properly written where all these summation terms one side, one by this and this value. So, what we are, why did we do this? Is it not YC value is actually depending on this feature map? So, YC value directly depends on what? On the activations inside the feature map. It is what the YC is depending. Right. Now, what is that we have computed from the previous from this particular slide? When an input image is being passed during a testing, already the CNN is well trained. So, if the CNN is trained, all of these weights are already been trained, right. So, now when an input image is passed, for that particular input image, some prediction will be for example, this is the this is where the class, the model predicts. Now, whichever class the model predicts, it is going to take only those weights. It is going to take only those weights. Now, once you take those weights, what is that you will do? We have the feature maps of final convolutional layer, right. So, these are the feature maps of a final convolutional layer. The next step is you have to produce the heat map. How is that you produce it? Now, the rest of the steps will remain the same as Grad-CAM, where there are feature maps and then there are weights. Only difference is the way the weights are calculated in Grad-CAM and the way the weights are taken for CAM is different here. So, in Grad-CAM we are taking the gradient matrix and we are computing the average, and for the CAMs here we are taking the for which class the prediction is made, its associated weights only. So, for a predicted class takes its fully connected weights, and the next step is multiply these weights with the feature map. Multiply the weights with the feature map, we get something like this, and then we are going to do the addition of each point wise, element wise addition we are going to do. By performing the element wise addition, we are going to get one feature map. And that feature map here is an heat map, and if that heat map is having some negative values, pass it to ReLU, so that you will have only positive values and 0. Higher the values in these are high importance, lower the values are low importance, 0 or negative if no ReLU is applied, which means there is no contribution. So, once you do, here also the last step is exactly same as the Grad-CAM. Here the feature map what we have obtained is smaller in size. So, the next step is you will up sample the heat map. So, if this is the original image, this is the Grad-CAM CAM heat map if it is produced. The next step you will resize it and then you will superimpose, and this is going to highlight which are the features. So, a quick summary of CAMs. So, CAM is a pure forward pass technique only. No gradients are computed, no back propagation here, nothing. So CNN model, when during a training you have back propagated, you have updated the weights, you have updated the kernel, all those are done during training. In the testing, you will just pass the input image, and input image will pass through, will go through the forward pass. By end of a forward pass, we are going to get the prediction for that particular input. Whatever the prediction, you will take the weights of only those classes. The class. So it takes the feature map from last convolution. It is going to use an global average pooling, and the weights connecting the global average pooling to final output neuron for the predicted class. No gradients are computed, no back propagation is performed in CAMs. Because the architecture is very restrictive, a special type of CNN here. What is the special type? It is just where there is only any number of the CNN is any number of convolutional layers, and then we have global average pooling, and then we just have one single fully connected. This is too restrictive. Therefore, the modern architectures doesn't use CAMs in order to find out the features that are important. Actually, this is the reason why Grad-CAM was invented. So, nowadays it is Grad-CAM that is used more than the CAMs. With this, we have come to an end of this particular session, where we have seen Grad-CAM and CAM's working mechanism. In the next session, that is towards the end of this particular week 5, you are seeing the hands-on implementation of XAI methods.